I've been asked a lot of questions about the changes in our 1970 engines. While some of the changes, like the distributor solenoid, the carburetor idle speed solenoid, and the heated air intake system are out in plain sight, many of the improvements are refinements that are hidden inside the engine. One of the common questions I hear is, why do we use these solenoids on some engines and not on others? Technicians also ask, how do these solenoids affect service and tune-up? So I decided it was time we got the answers to these and other questions you've been asking from a couple of experts on the subject of exhaust emission control. Let's see what we can learn from Bill and Don about clean combustion and emission control in our 1970 engines.
I think we can set the record straight on several things that are generally overlooked or misunderstood. For example, there are 3 basic ways to reduce undesirable exhaust emissions, those air pollutants that would come out of the tailpipe if we didn't do something about it. We could use a catalyst or exhaust gas afterburner to get rid of the unwanted gases before they reach the end of the tailpipe. But afterburners use extra fuel to complete the combustion process. Besides, they are complicated and expensive. Another way to keep it clean is to pump extra air into the hot exhaust gas as it leaves the exhaust ports. This completes the combustion process after the unburned portion of the mixture leaves the combustion chamber. A third approach to clean exhaust is to refine and improve the entire engine so that virtually all of the fuel fed into the engine is burned in the combustion chamber. And of course, complete combustion means clean exhaust.
From the outset, Chrysler has gone the clean-burning engine route. Year after year, we have improved our engines to reduce undesirable exhaust emissions.
Right, Tech. And for that reason, every engine model we build, from the 198 Slant 6 to the 440 V8, has different design characteristics. What's required in the way of ignition timing and carburation to make a Slant 6 run clean isn't the same as it is for a 318 or a 440. And last year's engines aren't necessarily the same as this year's engines, even if the displacement happens to be the same.
I guess that explains why we use an ignition retard solenoid on some engines and not on others, and why we have an idle speed solenoid on some carburetors and not on others.
It sure does, Tech. But I think we better review some of the basic facts about combustion and clean exhaust so everyone will understand why we use these solenoids on some of our engines.
Sounds like a good idea to me, Don.
Complete combustion and clean exhaust is the result of many things. The right combination of combustion chamber shape, compression ratio, camshaft design, manifolding, ignition timing, carburation, and engine operating temperature. In other words, clean combustion is something that is designed into our engines, not added on. All of our engines are inherently clean and efficient over a wide range of operating conditions. However, all engines tend to produce a higher concentration of undesirable exhaust products at closed throttle than they do under other operating conditions.
Why is that, Don?
I think I can illustrate why the relatively small amount of fuel supplied at closed throttle doesn't always burn clean. The circle at the left represents some flash powder spread over an area so that the combustible particles are close together. At the right, a smaller amount of powder is spread over the same area so that the particles are farther apart. Now, if a match were dropped into the powder where the particles are packed close together, poof, the flash powder would burn completely. There would be no unburned or partly burned particles left. If you ignited the powder that is spread out, the flame would fizzle out because the particles weren't close enough together to support continuous combustion. This is similar to what sometimes happens in an engine's combustion chamber at idle and when decelerating with closed throttle. You see, at closed throttle, the fuel particles aren't closely packed, and the flame tends to go out before all the fuel is burned.
Here's one way to clean up this condition. Have the throttle open a bit wider in the closed throttle position so that the engine can pull in more mixture on the intake stroke. Then, on compression, the fuel particles will be packed close enough together so the fire keeps burning. Combustion will be much more complete and cleaner. There's one little catch to this. Opening the throttle more to let in more mixture at idle could result in objectionably high idle speed on some engines. To compensate for this condition, we use the distributor with solenoid on some engines to retard the spark at idle so that combustion takes place later in the power stroke when the piston is literally running away from the expanding gas in the combustion chamber. Since there is less push on the piston, this is a very effective way to reduce engine idle speed.
In other words, you feed more mixture for complete burning at idle, and then use late ignition to reduce the mechanical power and engine speed. The net result is cleaner combustion and acceptable idle speed. But how does this combination affect combustion during deceleration?
Increased mixture flow at closed throttle promotes more complete combustion and cleaner exhaust during deceleration, just as it does at idle.
But a few years ago, we used a decel valve on some engines to advance ignition during deceleration, giving the mixture more time to burn. Retarding the ignition at closed throttle seems to be a contradiction.
The fact that the solenoid retards the ignition during deceleration results in higher exhaust gas temperatures, and burning continues during the exhaust stroke. This, combined with the increased mixture flow at closed throttle, results in more complete burning of the combustibles during deceleration, less chance of the fire going out before combustion is completed. Although some of our engines look the same and have the same displacement as past models, they are not the same internally. In order to do our part in promoting clean air, we are continually refining and improving every one of our engines. They are getting better and running cleaner every year.
Since Bill answered my last question, suppose you explain what the distributor solenoid does and how it works, Don.
Gladly, Tech. And there's more to it than meets the eye. The best way to understand what the solenoid does is to compare the advance curve of a distributor without solenoid with a distributor having a solenoid. This ignition advance curve is typical of distributors that are not equipped with a solenoid. Notice that the ignition does not advance during starting and at idle. Here the ignition advance curve of a distributor with solenoid is superimposed on the previous advance curve. Notice that the solenoid allows more advanced ignition timing for easier starting, immediate ignition retard for clean exhaust at idle, and immediate advance when the throttle is opened. The solenoid is built into the vacuum advance unit. When the solenoid windings are energized, they pull the armature inward, and this rotates the distributor breaker plate to the fully retarded ignition timing position. The switch that controls the distributor solenoid consists of the carburetor throttle stop and the curb idle adjusting screw. When the throttle is closed, the solenoid ground circuit is completed. The solenoid circuit is simple. The feed terminal is connected into the ignition circuit. The ground side of the circuit is connected to the stop for the curb idle adjusting screw.
One thing that puzzles a lot of technicians is this little plastic box attached to the vacuum advance unit.
That's a transistorized control unit, and it does a couple of things. The control unit does about the same thing that a relay does. It reduces current flow in the ground side of the circuit to eliminate any chance of arcing when the idle screw opens and closes the solenoid control circuit. In other words, the control unit permits all of the current flow needed through the solenoid windings to retard the ignition, but limits the amount of current flow through the idle stop and idle adjusting screw to a very low value. In addition, as soon as the solenoid pulls the armature into the retard position, the control unit reduces current flow through the solenoid windings to the minimum needed to hold the armature in.
You'd better explain why reduced holding current is a good feature.
If full pull-in current was allowed to flow through the solenoid windings whenever the throttle was closed, the solenoid might get pretty hot under prolonged engine idling. Cutting back the hold-in current eliminates this possibility. Since the vacuum advance unit with built-in solenoid and control unit is serviced as an assembly, you really don't have to worry about the internal circuitry of the solenoid or the control unit.
You two have answered all of the questions I've been asked about how the distributor solenoid works. Before you explain how the distributor solenoid affects tune-up and timing, why don't you explain the idle speed solenoid used on some of our 4-barrel carburetors? You'll have time to catch your breath while someone out there is turning the record to side number 2.
Our Hemis 340s and our high-performance 440s are a different breed of engine. It isn't likely that Aunt Minnie would choose one of them to haul the family groceries. Among other things, they're designed to idle at 800 RPMs or higher. Cars equipped with these engines are great open highway machines. The people who buy these jobs don't plan on spending a lot of time driving in heavy traffic or standing with engine idling in a rush hour traffic jam. However, because these high-performance engines do require much higher idle speeds, they tend to keep on running after the ignition is turned off. This is called after running, and one of the best ways to prevent it is to reduce the flow of air-fuel mixture. Now here's how that's done. The stem of a solenoid attached to the carburetor is used as a throttle stop for the fast curb idle speed screw. When the ignition is on, the solenoid is energized. The stem is extended and the idle adjusting screw seats against it to provide the specified curb idle speed. When the ignition is turned off, the solenoid stem retracts, allowing the throttle blades to close and cut down the flow of mixture. When this happens, the combustion temperature drops below the self-ignition point and the engine stops instead of after running.
There's nothing complicated about the operation of the idle speed solenoid. However, 3 idle speed screws are used on these carburetors, and the new names for these screws have caused some misunderstandings. So let's clear the air on that score right now. The fast idle speed setup is the same as on past models. It's still called the fast idle speed adjusting screw, and the adjusting procedure is the same as it was last year. The fast curb idle screw is the one that rests against the stem of the idle speed solenoid and adjusts idle speed to the specified warm engine idle speed. In other words, this is nothing more than a new name for the curb idle adjustment. Unfortunately, the curb idle screw doesn't really have anything to do with engine idle speed or keeping the engine running. On the contrary, it's the engine shutdown screw. It lets the throttle valves close far enough to prevent after running when the ignition is shut off, but keeps them from closing all the way and jamming in the throttle bores. Adjustment of both idle screws is simple. Adjust the fast curb idle screw to obtain specified curb idle speed. Next, turn the curb idle screw in until it just touches its stop, then back it off 1 turn. And that's all there is to it. Of course, to prevent after running, it's equally important to set idle speed correctly on jobs not equipped with a carburetor solenoid.
It sure is, Tech. Now, for 1970, most engine models have a heated air intake system. This is a very important improvement from the standpoint of warm-up performance and reduced exhaust emissions. By feeding the engine heated air in cold weather, we were able to design our engines, calibrate carburation, and establish ignition timing for good, clean combustion at moderate temperatures instead of compromising to cover a wide range of temperatures. The heated air intake is an air blending system. A vacuum-actuated heat control door in the air cleaner inlet mixes unheated and heated air in the right proportion to maintain correct intake air temperature. Vacuum to the heat door diaphragm is thermostatically controlled so that more heated air is blended with the unheated air in cold weather, less heated air in warm weather. An exhaust manifold stove provides the heated air source.
Although the heated air intake system is a very important part of the clean combustion story, we're going to save the detailed explanation of how the several different versions of the system work and the service information until next month. Our next session will also cover the vapor saver system, which keeps fuel vapors from escaping into the atmosphere. This is just another way in which Chrysler is doing its part to keep the air we breathe clean. And now, what words of wisdom do you two have about setting the ignition timing and checking the dwell on a car equipped with a distributor solenoid?
I have 4 key words, Tech. Use your service manuals. But I better explain what kind of trouble you can get into if you don't. Timing specifications are based on a fully retarded distributor, no vacuum advance, and the breaker plate pushed into the fully retarded position by the distributor solenoid. When checking or adjusting timing, the engine must be fully warmed up. The idle speed and mixture adjustment must be correct, and the fast curb idle screw must be seated so that the solenoid ground circuit is completed. Before checking timing, disconnect the distributor vacuum advance hose and plug it. Leave the distributor solenoid connected.
Never try to disconnect either of those leads from the solenoid control unit. If you try to pull them off, you'll ruin the control unit.
Right, Tech. And when setting timing, grasp the distributor housing, not the vacuum advance unit. Using the vacuum advance unit for a turning handle could upset the calibration of the vacuum advance curve. To check distributor solenoid operation, disconnect the solenoid ground lead connector near the carburetor so that the solenoid is no longer energized. Timing should advance at least 5 degrees, and engine speed should increase. Next, reconnect the solenoid ground lead. Timing should retard. Move back to the specified timing mark and engine speed should decrease. Reconnect the vacuum advance hose. Engine speed should not increase and timing should not advance. If timing advances, it's because the throttle blade has uncovered the vacuum advance port. This means that idle mixture and speed are not correctly adjusted.
Incidentally, if the throttle blade uncovers the vacuum advance port at idle, the distributor solenoid will not retard the ignition at closed throttle. That's because the pull of the solenoid is not great enough to overcome the pull of the vacuum advance unit. Another thing, I've heard of technicians who disconnected both the vacuum advance unit and the solenoid and then set timing 10 or 12 degrees before top dead center. Don't do it. You could blow an engine.
Why is that?
If the disconnected solenoid happened to be stuck in the retarded position, timing could advance as much as 10 degrees when the solenoid got unstuck. This could give a basic timing in the neighborhood of 20 degrees before top center. That could put holes in the pistons and cause other serious damage. Another mistake is to assume that you can check solenoid operation by removing the distributor cap and watching for breaker plate movement as you disconnect and connect a solenoid lead. This test is not reliable for a couple of reasons. The breaker plate may not be moved by the solenoid if the ignition point rubbing block happens to be on one of the cam lobe ramps. Besides, since solenoid movement is less than 1/16 of an inch, it isn't easy to check it.
I've been asked if the addition of the solenoid affects cam dwell in any way.
It sure does, Tech. Dwell specifications are based on no vacuum advance, no solenoid retard. Before checking dwell, both the vacuum hose and the solenoid lead must be disconnected. But let me explain why this is so important. We set dwell with no solenoid retard so that it will be correct for all off-idle driving conditions. If you set dwell to specifications with the solenoid connected, it would not be correct under actual driving conditions and performance would suffer.
I have one more question before we sign off. The service manuals mention that the compression ratio has been reduced on all of our 8s, except high-performance engines. Some technicians think this is a step backward. Can you explain why it isn't?
Gladly, Tech. As we pointed out earlier, compression ratio is only one of the many factors affecting engine efficiency, power output, and exhaust cleanliness. Within a reasonable range, it isn't even the most important factor. Just remember, the net result of recent improvements in combustion chamber shape, camshaft design, manifolding, ignition, and carburation is more complete combustion and cleaner running engines.
You two have answered all of the questions I've been asked by our master technicians and then some. And now, I want to remind all of you technicians out there that I'll be back next month to tell you more about the things Chrysler is doing to keep it clean. So don't miss our next session when we'll cover the heated air intake system in detail and tell you all about the new Vapor Saver system.